Hi, this is an example problem from Chapter 16 on the mathematical properties of a traveling wave. Pause for a moment and read the question. So we're given a specific equation here that describes the position of a wave on the y-axis as a function of the position in space on the x-axis and the time t. We're going to solve all of these questions here by using the general equation for the mathematical form of a traveling wave and comparing with this specific equation with that general equation. So here's the general equations. First of all, there's the wave could be traveling to the right. There's a minus sign here. Or it could be traveling to the left. There's a plus sign there. We see the plus sign. We know it's traveling to the left. Let's go ahead and copy this and just go ahead and put it into the video. And remember, important warning here. You must use radian mode when you're dealing with this, when you use the trig functions. So there's the general form of our equation. Part A, what direction is the wave traveling? Well, we just saw because of the plus sign, it is traveling to the left. In part B, we're going to figure out the angular frequency, and C, we're going to figure out the wavelength. So for the frequency, angular frequency, we know that's related to the period here, and that's the general form of the equation. In our specific equation, we see, well, we've rearranged these in different order, but that's the term by t, right? So we can set those two equal. In other words, 2 pi over t is equal to 1 divided by 0.2 seconds. Now we can do some algebra or just cross multiply to solve for t. And we find that t is equal to 0.2 seconds times 2 pi. And I'm not going to calculate that just yet because we're actually solving for the angular frequency here, which is omega. And recall the frequency period relations. Omega is equal to 2 pi times the ordinary frequency, which is equal to 2 pi divided by t, right? So if we want to go ahead and plug these values in, we're going to get 2 pi divided by t is equal to, we saw, 0.2 seconds multiplied by 2 pi. The 2 pi's, of course, will cancel out, and we're left with 1 divided by 0.2 seconds, which is equal to 5 per second. In fact, this is an angular frequency, so that's 5 rads per second. Now, to solve for the wavelength, we're going to compare with what we see here. So notice how 2 pi is one complete cycle, right, of an oscillation in radians. And t is the time for a complete cycle. That, of course, goes with t. In this case, 2 pi, a complete cycle. Lambda, that is the length in space of one complete oscillation, right? So if you're looking at like an oscillation peak to peak, right? There's your lambda. And again, we're going to use the same method as before. So 2 pi over lambda from the general equation, right, over here, is given by the specific equation. That's also multiplied by x, so we can set those equal. 2 pi 2.4 meters. And in fact, this one we can go ahead and calculate quite simply because the 2 pi's cancel, take the reciprocal, and you'll find immediately that the wavelength in this case is equal to 2.4 meters. And so the wavelength and the period, they play similar roles. One is for time, total time for a complete oscillation. The other one is for length, the distance in space of one complete oscillation. Moving on to part D, we're going to go ahead and just use the fundamental equation that relates the speed of a wave to its wavelength and its frequency. V equals lambda times f. That's going to be 2.4 meters multiplied by, I need the frequency now, so I actually need to calculate f, which is going to be let's see, F is omega over 2 pi, so 5 rad per second divided by 2 pi. And that, of course, comes from the fact that omega is equal to 2 pi F. F equals omega over 2 pi. And that gives us a value of 1.91 meters per second. And again, we drop the rads because we've multiplied by meters. All right, let's move on here. Part E, what is the tension in the string? So for this one, we're going to need to use the equation that tells us what is the speed of a traveling wave on a string. That equation, the speed of the wave, is equal to the force of tension that the string is experiencing divided by the linear mass density of the string. Now, the linear mass density in your book, they write it as the mass of string divided by the length of string, but it's really just a single number, and so these two speeds, right, in this case, these are the same for the wave on a string, and this lower one tells us what the speed is in terms of the basic properties of the string. It's the tension and the linear mass density. Now, we are given the linear mass density in the problem. We are told here it is equal to 0.5 kilograms per meter. So all we need to do is solve for the tension from this equation. Let's square both sides, and we're going to end up with Ft over the linear mass density is equal to V squared. And finally, we can go ahead and multiply by mu on both sides to get this equation. And when we plug in the numbers, we'll get our answer here. 0.005 kilograms per meter multiplied by the wave speed squared. And that's going to give us a value of tension of about 0.018 newtons. And that makes sense because we've got units wise here. We've got kilogram per meter, meters squared per second squared. We cancel one of those meters. Kilogram meter per second squared is in Newton. Good. All right, so now we're going to look at what are the magnitudes of the maximum displacement, maximum speed, and maximum acceleration of a small segment of the string. In other words, a particle of the string, it's going to be oscillating up and down. So here is maybe a little portion of the string here, right? My little picture that I drew. That little portion, it's going to oscillate back and forth, up and down, vertically in simple harmonic motion. And we want to go ahead and calculate the max values for displacement, speed, and acceleration, the magnitudes. Now, we've done this before. We just need to go ahead and look up the equations of motion for simple harmonic motion. And if we recall, now these are written here for traveling waves, but these are just equations of motion for simple harmonic motion. Actually, we've just switched the cosine and sine for these to make it agree with the wave equation, but it's the same thing, same frequency, period relations. Again, for the max displacement, it's the amplitude. Max velocity magnitude is a times the angular frequency, and for acceleration magnitude, a times angular frequency squared. So I should call this y max in this case for going up and down, right? So we already know what omega is here. We calculated it. All we need to do is look up and see what is the amplitude. Let's go back to our general equation here and have a look. So the amplitude is 3 centimeters or 0.03 meters. So there is your 0.03 meters. There's your maximum displacement magnitude. Here we're going to have 0.03 meters, 0.03 meters, and multiplied by omega, which is 5 rad per second. And for the acceleration, we're going to square that. When we do that, we come out with some answers. 0.15 meters per second max speed, and for the acceleration, 0.75 meters per second squared. And again, of course, since we multiplied by meters, we drop the radians there. Finally, part I, at a time t equals 3 seconds, what is the displacement of a small segment of the string located at x equals 0.5 meters? What we need to do here now is evaluate the specific equation for y, the position of a part of the spring, at a particular location in space. X is equal to 0.5 meters, and the time is 3 seconds. So we need to just go ahead and write down the general equation here and plug in those numbers. So let's go ahead and do it. We're going to have 0.03 meters multiplied by sine, and the argument, it is 2 pi over 2.4 meters. Now multiplied by x, that's your 0.5 meters here, plus 1 divided by 0.2 seconds, multiplied by t, that is your 3 seconds here. Now be sure to use your calculator in radian mode, and when you calculate this, it comes out to of minus 0.017 meters.